Let's talk about statistics for measurement uncertainty more specifically, and why do we need to bother with statistics. I like statistics quotes. Some of them are quite dry in their sense of humour, and this one from George Canning is a good one. I think that I can prove anything with statistics except the truth. And while that's quite tongue-in-cheek, it's actually very factually correct, because inherent in all statistical methodologies and conclusions that we come from statistics is uncertainty. And we know in measurement uncertainty we are trying to do an estimate of a result which we've measured, with the proviso that we know that we can't ever determine the true value. So this quote's actually very, very accurate in what it says, in that we can't ever prove what the truth of that estimated measurement is, but we can give some sort of indication about how confident we are, or what the meaning of that result in the context of the way it was taken actually is. Here are the objectives that we're going to cover in this lecture. So familiarity with statistical concepts, identify some methods, and try and generate some confidence are the objectives that we're aiming for. And hopefully the outcomes for you viewing this lecture will be that you do understand some of the terminology that's used, and once you've gained that knowledge, you can then apply that knowledge to data that you have, using some of the basic methods and advanced methods that we're going to continue with throughout the course. So let's start at the beginning. Why do we need to bother with statistics at all? Well, we need to describe our data. And by describing our data for measurement uncertainty, and in fact any data that we generate in the laboratory as a whole, it helps us with making predictions. And predictions are useful to us in the laboratory, whether that's predicting whether somebody has a disease, or whether predicting somebody is getting better or worse. And statistics is a science that's been born out of that need, that requirement really, to be able to make predictions and generalizations based on samples of data. And the laws of statistics which have been developed help us understand measurement uncertainty. Hopefully, I've said in brackets there, and we'll see as the course goes through. Hopefully that will certainly come to be the case. A lot of the terminology which is used is unfamiliar to us, and by learning about statistics in general, the terminology that's used in measurement uncertainty becomes more familiar as well. It's a huge topic. To try and do a quick snapshot of what statistics means and what that means in the context of measurement uncertainty is a bit of a huge task. So this is just a quick, brief overview. If need be, I could have made a 3-day course on this just alone, but we will not go into that much depth. It will take as much time as that. So in general, statistics are tasked with comparing hypotheses against experimentally produced data. So all hypothesis that we have, that we generate, is based on data that we have measured. And that's something we're familiar with in the clinical laboratory. And by using statistics, we have a standardized language, if you like, that we can use to be able to test those hypotheses and to report and present the findings in a way that's easily understandable, irrespective of the background scientifically of the person reading the conclusions. Statistics may be thought of as, at a first glance, as a single concept, as a single idea, but there's lots of different ways that statistic can be applied. It's very importantly, it's not just p-values. And p-values is something that we absolutely associate with statistics, rightly or wrongly, and I think you'll gauge my opinions on that as we progress through the module. But in order for statistics to be effective and for it to be useful, we have to take a number of steps which actually can all fall under the umbrella of statistics in general as well. The first of which in the table below you can see is the scientific collection of data. How we design our experiments, what data we're going to generate, what format that's going to be in, will absolutely influence the conclusions that we're going to be able to make at the end. It's, dare I say, a frustration of mine that quite often people will come to me with a spreadsheet full of messy data, and say, what tests can I run on this to get a decent p-value? And by that time, I'm afraid it's a little bit too late. If we haven't put the effort in to try and collect the data in an appropriate way, it's going to be incredibly difficult to find any meaningful conclusions. And it's also good scientific practice to, before you do any testing or any measurements, to actually know what you're looking for or the questions you're trying to answer so that you do design it appropriately. Once you've done that, you need to be able to organize the data into a useful format. And the format that's most familiar to us in the lab is tabular format. So nicely structured rows and columns, variables in the columns, and entities or individual measurements in each row, so that we can summarize the data easily. Which leads on to the method of analysis, which is the start of the process of extracting insights. And we do that by numerically describing what is contained within that data that we have collected and that we've organized properly. But once we've got results, it doesn't end there. We need to know how we should present the data most effectively, be that again in summary tables and graphs and charts, so that the hard work that we've done in the background using the statistics can be looked at by the viewer very quickly, and the insights can be drawn very quickly and meaningfully as well. And of course, the final part of any project write-up or anything will be the interpretation and the discussions and conclusions of those results which have been generated, which is all dependent on each of those previous steps. But for the analytical step, there's no such thing as statistics, if you like. There are different branches of statistics, and these have been born throughout history over a number of years, over a few hundred years. And although trying to work towards the same end, the interpretation and the generation and confirmation of scientific hypotheses, the roadmaps that they take to get there are somewhat different. And we'll just touch on mentioning them just now. We will discuss these in a lot more depth throughout this module, and also in the advanced module we'll talk about them as well. But generally speaking, the branches of statistics are the classical, frequentist, which is probably the most familiar method to everybody that we use most often nowadays because that's what we get taught, and also the Bayesian methodology, which I think conceptually speaks to us in clinical laboratory science a little bit more, because it talks about developing, using data to develop knowledge that we already have, and that's something that is very, very familiar to us in a clinical laboratory. A fundamental concept, irrespective of which of the branches of statistics you use, is the realization of the difference between a population and a sample. And if you think scientifically, what we're trying to do with statistics as a whole is that we are sampling or we're doing experimental data on a small sample of, be it plasma or patients or whatever, and we're trying to make conclusions that we can generalize to the entire population. The population is what exists if we have all available data available to us, and that really, really doesn't happen very often. Chance would be a fine thing. We very rarely have the ability to collect all of our data from the entire population, so by necessity we do a sample and we try and extrapolate our data from that sample to the greater population as a whole, and we use that as a representation of the population. Now, of course, when we're using a sample, that generates uncertainty, and the methodology that we use for sampling actually has a specific uncertainty contributor as well, and we will come to that. But either way, what we're trying to do is do a sample selection that will represent our population adequately and try and statistically describe them numerically using something called parameters, so that those parameters can be applied to any other sample or the population as a whole to understand the findings that we've made. So parameters, that was our first statistical jargon word that came out so far in this talk. What does that actually mean? And as I alluded to, it's a numerical representation that defines a system. That means that the condition of its operations of the parameter defines how that system works. That's quite a heavy description. So let's try another one of a quantity whose value is selected for the particular circumstances. Very important, the circumstances of the data collection and the sample has been taken, so that it can be applied in relation to other variable quantities that may be expressed, so other data sets. It's generally a numerical characteristic of a population, which is distinct from the statistics of the sample from which it is derived. Statistic itself has a meaning. A statistic is, generally speaking, particularly if we're talking about hypothesis testing, as a number and a value against which we can compare a standard value or a range of standard values to determine whether something is above or below the threshold. A statistic in general is a fact or a piece of data, and it can be any of a number of numerical representations of a data set. So if you think you do a given test on 100 patients and you calculate what the mean value is, the mean would be a statistic, and that mean has a meaning with respect to that sample, and it has a meaning that we could then extrapolate to the population. Types of statistics may include, as I've already mentioned, descriptive statistics like the mean, the standard deviation, the variance, the median, the interquartile range, and they summarize all the raw data into one single measure, which really identifies the characteristics of that data set, so that if somebody gives you that number, you can start already in your mind drawing some conclusions about what is actually happening within that data set. And from those descriptive statistics, we can move to the next step and start using a different kind of statistics called inferential statistics, which try and explain what the data mean, and in which case that inferential statistics are defined as explanatory because they're explaining. And often we're taught that as by doing hypothesis tests, so things like ANOVAs, t-tests, things like that. And that really comes from the frequentist paradigm, whereas the Bayesian paradigm will use probabilistic measures of what the inferences we can draw from the sample of data mean. And by inferences we mean, generally speaking, extrapolations, making conclusions about a population when we only have a limited data set that we've managed to perform the measurements on. So let's get to the nuts and bolts. What statistics do we actually need for measurement uncertainty? We need a measure of the centrality of the data, so means, medians, modes. A measure of the spread of the data, so the interquartile range, the variance, the standard deviation. Characteristics of the data and distributions of the data, and characteristics of those distributions, things like skewness and kurtosis, whether the distribution of the data can be described as a normal distribution or a log normal distribution, or any of the other kinds that we'll discuss in a later lecture. That concludes the introduction of why we use statistics for measurement uncertainty and what some of the statistical measures are. They are unavoidable, they're not that difficult, and we're very familiar with a lot of the terms that we've already mentioned in this lecture. They're generally describing or summarizing the raw data. If we take 1,000 measurements of something, it doesn't make any sense for us to scroll through that entire spreadsheet and try and make inferences on those individual measurements. And actually, thinking about measurement uncertainty, that doesn't make much sense either, does it? So what we do is we summarize that data set so we can then move to the next step of using inferential testing statistics as well. We're going to move on now and talk about some of the notational definitions that are used, generally in mathematics and in statistics, and particularly how they apply to measurement uncertainty.